So I have introduced this new type of line integral, which includes a dot product, and now I'm going to give you an example of an application for this, okay? And the typical example that is always given in books is the work done by a force over a path, okay? So let me explain this carefully. Imagine that we have a constant force acting over a straight line path, okay? So for example, we are moving an object from here to here, okay? And this along a straight line. So this is a straight line, yeah? And we have a force, for example, the force of gravity. So the force of gravity is constant everywhere, right? Let's assume we are on the surface of the Earth and that the height is negligible with respect to the radius of the Earth. So we have a constant force acting downwards, okay? So this is our force. So what is the work done by this movement? So what is the work done by gravity when the mass undergoes this movement? So one thing we can do is we can define this vector, and we can call this vector delta r, okay? The vector pointing from the initial point to the final point. So now you know that the work is equal to F vector dot delta r, right? You have to do the dot product because only the component of the movement in the direction of the force counts towards the work, right? So you remember that in special cases, for example, if you are moving a mass directly downwards, so delta r is this vector pointing down in the same direction as the gravity. So then the work done is simply F times the magnitude of delta r without vectors, yeah? Because the dot product between both is just the norm of one times the norm of the other times the cosine of the angle between them. And in this case, the cosine of the angle between them is the cosine of 0 degrees, which is 1. So you can write it like this. And for example, if you are moving a mass horizontally, so that delta r is this horizontal vector, and the gravity is acting downwards, F, throughout the path. So then the dot product of this vector with F is 0, and therefore the work done is 0, okay? So you know that. And all of this is summarized in this simple equation. Now, what if the movement is not along a straight path and the force is not constant? Okay, so for example, we have this crazy path, yeah, and our force is not constant, meaning that if I now start drawing our force, so at each point along the path, our force is changing. Okay, so maybe this is, I don't know what kind of force it could be. Maybe this is an electric force, and we have a strange electric field which depends on position. So how can we calculate the total work done following this path C and with this force which depends on position, F of r? Okay. So the way we can do it is by cutting the path into tiny segments. Okay, so for example, we zoom in here. Okay, we are zooming in. So if you zoom in, let's do this like a zoom in. Actually, let's exaggerate this. We are zooming much more. We are zooming in into a tiny region. Okay. Because we are going to divide this path into differentials. So now we are looking with this magnifying glass. So now the path is a straight line. And the force, since we are zooming in so much, the force is constant everywhere, right? Because it doesn't have time to change if we zoom in far enough, okay? And therefore we can define a differential of work along this path given by this differential of the path. So let's call this dr, and this is the force evaluated at r. So now the differential of work is just the force evaluated at R dot dr, because everything is constant, by zooming in closely enough, okay? But in reality, we are getting a tiny differential dr, right? So for each tiny differential dr, we are getting a differential of work. So now this is great because the total work is simply the line integral of the differential of work, which is the integral of f dot dr, which is exactly the type of integrals that we are going to be talking about in the rest of the chapter. Okay? So this is the famous example of why we need to do this type of integrals to calculate the work done. Another famous example is Maxwell equations. So there are lots of times that you have to do, for example, B, the magnetic field dot dr, right? In Ampere's law, for example. And in general, there are many laws in physics in which this type of integral pops up. Okay, so it's very important that you know how to solve it. See you in the next video.